Hello everyone, welcome to this session. In the previous sessions, you have learned most of the concepts in optimization. In this session, we will talk about formulate engineering problems to optimization problems. So why we need to learn this? Because to apply AI techniques for optimization into real problems, you first need to formulate them to optimization problems, then you can use the AI tools. So in this session, we will talk about the procedures to formulate an engineering problem to an optimization problem. So here I use an engineering problem, but the general science problem, we follow the same way, right? So this session, we will talk about a real case that we have done before, right? So let's see, the procedures are as follows. Step 1, we need to identify the requirements from the engineering problem. So what are the requirements? Second, knowing this, we try to classify the requirements to objectives and constraints. Then we need to identify the decision variables and their properties. So we know what the problem is, right? What kind of optimization problem is after step 1 to step 3. Then we need to identify the search space. After that, we can ask if there is a starting point. Then we can identify how to obtain the objective function and the constraint function values. So these are the 6 general steps. After knowing these 6 steps, you should be able to define an optimization problem from an engineering problem. So here we talk about an engineering design problem, which I will show you later by a case study. The problem is like this. We need to design an 8th order microstrip filter. So as you can see is here. So the operating frequency is 3.3 to 7.3 gigahertz. The designer comes to you for consultancy, and you are an engineer armed with AI techniques for optimization. So now you receive this problem. Clearly this problem is quite weak now, right? So now we need to use step 1 to step 6 to formulate this to an optimization problem. So you can communicate, assuming you are the consultant, you will communicate with the engineer, right? For step 1, identify the requirements. So you can ask, so what are the design requirements? The designers will say, okay, the passband is 4 gigahertz to 7 gigahertz, and we have 2 stop bands. One is from 3.3 to 3.92, and the other one is from 3.08 to 7.3 gigahertz, right? So this could be the engineer's response without knowing this knowledge. This is just their bare design specifications. But however, maybe you don't understand, so what is passband, what is stop band, right? So then you can ask, could you please detail the requirements? Then he can maybe tell you, okay, for the passband, the maximum of the magnitude of the S11 should be smaller than or equal to minus 20 dB for passband. And for stop band, the minimum of the magnitude of S11 should be larger than or equal to minus 3 dB for the 2 stop bands. Okay, now this is better, right? So now at least there are some specifications there, right? But however, this one we still can't formulate it to objective and constraints. So then we need to ask more, right? So you may ask, could you please write your requirements as constraints? So for constraints, I mean that you can explain what is constraint. So after knowing these concepts, the designer may provide you, okay, passband max S11 smaller than or equal to minus 20 dB, stop band min S11 both consider magnitude larger than minus 3 dB, right? So this is the specifications. So now the specifications are clear, right? So now you can say, okay, I got it. Now we can go to the step 2 because the requirements is already identified as here, right? You can see here. So step 2 is to do what? To classify the requirements to objectives and constraints. So then you can ask the designer, for these requirements, are there objectives So for objectives, I mean what also you can explain to him what is objective and the difference between objective and constraint, that the designers can understand. He said, okay, for the passband requirement, the smaller the better. For the stopband, meeting the spec is fine. So this means what? This means the passband requirement can be set as an objective. For the stopband, we can just set it as a constraint, right? So you can tell him, okay, your problem has one objective and two constraints. Or it's a single objective constraint optimization problem. Okay, then the step 2 finished. In step 3, that we need to identify the design variables and their properties, right? So we can say, what can you control in your problem? So we call them the design variables. So let me explain, so you can explain more about the definitions of design variables and the different kinds of them. The real number ones, the binary ones, or the permutation ones, right? So then the designer will answer you. So he will say, okay, there was 12 design variables, and they are geometric parameters, and I have shown you in the figure. So okay, then you can understand, okay, this is your 12 real value based design variables. So you want to optimize this. And you have the objective and you have the constraints. So step 4 is to identify the search space. So you may ask, okay, could you please provide the search ranges of your decision variables? So we can say, we can't optimize in that infinite space. There must be a search range. So outside the search range, the optimal design is impossible to locate there, right? Then the designer can provide you one. He said, okay, here you go. This is a table for the design variables. There's an upper bound, there's a lower bound. So smaller than the upper bound, or larger than smaller than the lower bound, or larger than the upper bound, the optimal design won't be possible, according to his engineering domain knowledge, right? That step 4 finished. Next step, we can ask if there is a starting point. You can ask him if there is a starting point. Using the starting point, the optimization may run faster because useful information, that is the starting point, is provided. Sometimes there is, sometimes there is not. And in this case, there is. The designer said, okay, yes, we do have one. This can be obtained by the equivalent circuits. So that he can provide you a starting point by the equivalent circuit method. So for the starting point of this optimization problem, then you can say, okay, now the optimization problem is set. Last step, we need to identify how to obtain the objective and the constraint functions values, right? So we can't, in engineering, most of them, which we can't calculate them by writing some simple analytical equations, right? So we need to, for example, this case, you can say, before optimizing it to meet your requirements, we need to know the way to obtain the objective and constraint values for each candidate design. So how can you do that? The designer say, okay, these values we extracted from the S parameters. So to get the S parameters, we need electromagnetic simulations. Okay, then you can tell him, okay, it's a simulation-based optimization problem, which is widely appeared in engineering. So we will link your simulation tool and find an appropriate optimization algorithm for you. Then your first period of consultancy finished. Then for the how to link with simulation tool and how to find appropriate algorithm, it goes to the next step. So we will teach in the future classes. Then after step 6, you need to model an engineering problem by computer program. So you may use MATLAB toolboxes. So MATLAB provide quite a lot of toolboxes. For example, here I listed a few: signal processing, RF toolbox. This can do simulations, right? Or you can use other simulation tools. So if you are a microelectronic engineer, later you will use SPICE tools, right? This is for circuit simulation. Then you need to program the objective function and the constraints, and by extracting necessary information from the simulation result. Then you can select an optimization algorithm, the set of optimization algorithm, and you can write, and you get the optimization result. Then you need to analyze the result and provide the designer the outcome, right? So for this example, this is a real example. So we can, after the first step, we defined this optimization function. So we can have a maximum, the magnitude of maximum one in the pass one, and have two constraints of the stop one. So these are the design variables, and this lower bound and upper bound, and also with a initial design. We call it the starting point in optimization. So after the initial design, so it's here, right? So then we can select an algorithm to optimize it, which you will learn in the next week, right? And the week after next. This is a initial design. This is the optimal design. We can see the optimal design almost meet the constraints, and the objective is much better than the initial design, and almost meet the design requirements, right? So this is in this session we use a case study to discuss how to transform a real-world problem to an optimization problem, setting the foundation for you to use AI techniques to solve it. Okay, thank you very much. That is all for this session. Bye-bye.